We'll now go ahead and move on to the second part of this practice set. In the first set, we talked about how to use the z-table and how to look at areas which correspond to probabilities. We looked at how to find areas from the left, areas to the right, and areas in between two values. Now we're going to generalize this and talk about using the normal distribution and the z-table, but for specific data sets. So in particular, we will actually look at how to go from raw data to z-scores, and we will actually call this standardization, standardizing the data. That means we're going to move from, say, some distribution x, well, in particular, some normal distribution x with some mean mu, and we're going to transform this into something, well, a particular something with mean 0, the standard deviation 1, the standard normal distribution, the z distribution, if you will. And we do this with means of a transformation that I have written here. If I have a data point x that comes from a normal distribution with mean mu and standard deviation sigma, then this transformation here, this formula, tells me how to go from x to z. X minus mu over sigma. This formula is key in this course, and we will see it crop up many, many times. We will actually use this to get from x scores to z scores so that we can actually use the z-table, because without it, we would need uncountably many normal distribution tables. And so we only want to use one table, the z-table, and that's why we have this transformation to go to z-scores. Now, as a challenge, I encourage you to solve this for x, meaning, can you take this formula and solve for x? This is the so-called inversion formula that allows us to go from z-scores back into x. And so let's actually get started with a few key examples here. Now, in these pictures, we're not going to have the tables printed on the page. You'll have to refer to them either on your screen or in a printed copy or the back of the text. So let's look at this situation here. Suppose that scores on a certain exam follow a normal distribution with mean 520 and standard deviation 65. Now, note the key part here, normal distribution. We are only talking about normal distributions here. You can't quite use the z-score transformation to go from any distribution to a normal distribution, only from normal to normal. So we have data here, so let's actually jot this down here on the side. I know that the mean score for this exam is 520, and the standard deviation is 65. And I want to find the z-score corresponding to an exam score of 730. So the 730 is a data point from this distribution, and we'll call that our x. So for part A, we need to figure out what an exam score of 730 looks like in the z distribution. Now, obviously, 730 is bigger than 520, so it should be to the right of the mean. So if I use this picture here, but instead ignore the f of z here and the z here, instead this is x and the density of x, which we don't need in this course. The mean here is 520, and the specific score that we're looking at is a score of 730, which is right here. So that's a score of 730. And so I need to find the z-score corresponding to that. So we look at our transformation, our nice formula here to get z-scores, x minus mu over sigma. And notice in the numerator, the order is important there. It's okay to have minuses, obviously. But remember, it's x minus mu over sigma, which we'll see later. I will refer to this looking at observed minus expected. Think about a score that you see and the average score, what you expect. So here, if we look at our formula here, we just plug things in. So z, let's make that better looking z here. Z is going to be equal to x minus mu, so x is 730, minus mu, which is 520, over 65. Okay, let's actually evaluate the numerator first. 730 minus 520 is 210. Divide that by 65, and we'll round to 2 decimal places here. 210 divided by 65 to 2 decimal places is 3.23. So that's the first part answered. We have the z-score. A score of 730 corresponds to a z-score of 3.23. So I'll mark this down here in this orange color here, that this 730 corresponds to 3.23. Now I want to find the probability that someone scores at least 730 on this exam. Well, at least means that score or higher, so I want this area to the right in orange. And so to get that probability, we will think about what we did before. Now, let's cast this problem in some inequality language. I want the probability that someone's score, let's say x, is bigger than 730. Well, we already transformed x to z, so remember that now we're looking to see what's the probability the z-score now is bigger than 3.23. So that's an area to the right. And to get an area to the right, if you remember from the last set, we will need to do 1 minus the area to the left of this thing. Okay, the entire area is 1. We take away what we don't need here in the blank part, here in white, and that gives us the area in orange. So this is 1 minus this probability. And we'll go ahead and look this up in our table, which we have handy. Mine is just off camera on paper. And it turns out that the probability, the area we need is 0.0, oops, got ahead of myself here, 0.99, let's see, 9994. Okay. And now we do the subtraction. This is 0.0006. There is a 0.0006 probability that someone scores higher than 730 on this exam. If you want to cast this into percentages, this is a 0.06% chance that someone scores 730 or higher on this exam. In other words, there is a 6 in 10,000 chance of making that score on this exam. So notice what we did here. We took a raw data score, cast that into a z-score, and use that to find a certain area with the tools that we have handy. And so now let's move on to the next example, which is a little more involved. So this example is motivated by scientific measurement. When we have an object that says it's a certain length, or in fact a certain mass, or is a certain volume, and it gets stamped on there, there may be, of course, variations in manufacture. For example, not all 20-ounce soda bottles have 20 ounces of soda in them. Not all liters of rubbing alcohol contain exactly 1 liter of rubbing alcohol. There is a tolerance in there. And so here, this question asks about a mass that is marked to have a mass of 12 grams. So the mass has 12 grams stamped on it. And then we want to measure it to see if that measurement is accurate. And the measurements that we record follow a normal distribution with mean 12.03 grams and standard deviation 0.04 grams. So let's actually gather some of the information that we have here in the preamble. And let's do this in red. So this is a facet of problem solving and getting to know information that you need. The 12 grams there is, in fact, a throw off. We won't actually need that. What we just need is the average mass that we record. In this case, the mean here is 12.03, and the standard deviation is 0.04. The question will tell you everything that you need. There is no need to search any deeper than you need to. No need to have any question of it. The question tells you exactly what measurements you have. So we have two questions here. Part A says to find the corresponding z-score for a measurement of 11.98 grams. So in this case, 11.98 plays the role of our x. That is the data point that we're looking at, and we want to get an associated z-score. So we have z equals x 11.98 minus mu 12.03. Let's clean that up a little. And divide that by 0.04. And remember the formula that we're using. Z is x minus mu over sigma. So let's go through this. In the numerator, 11.98 minus 12.03, that gives us minus 0.05 divided by 0.04. And when we do that, being careful with the minus sign there and our decimal points, we should get, we should get minus 1.25. So that's the associated z-score for that measurement. And let's actually mark that on our picture here. So this here is 11.98 grams. The mean is 12.03. Okay. And now, in blue underneath, well, the mean here in the center is 0. This is minus 1.25. And now we need to go to the next one, the corresponding z-score for a measurement of 12.08 grams. So now this time 12.08 plays the role of our x. So we do the same thing. Z equals 12.08 minus 12.03 divided by 0.04. On top, we should get 12.08 minus 12.03. That's 0.05 divided by 0.04. And when we do the division, that's a positive 1.25. Notice that this guy and this guy are the same in magnitude, but different signs. So here I will have 12.08 grams. That's from my actual distribution. But in blue underneath, we have the z-score for it, 1.25. And so now we're going to ask this question here. How likely is it that that a certain mass from, say, a sample of these, how likely is it that it measures between 11.98 grams and 12.08 grams? So in other words, I want to find the area inside this band in red. So that's one of our in-between areas that we saw last time. And so we'll have to use the same strategy here. So if you recall, the way we get this in-between area, we look at the boundaries here, the bounds here. We look at the area to the left that corresponds for the higher value, and then take away the value that corresponds for the lower value. So for part C here, I'm being asked the probability that a mass measures between 11.98 grams, that's there on the bottom, and 12.08 grams, that's on the top. Now, this is an x, and we already transformed this to z. We have the z-scores here in blue, which I'll change here. This is the probability that now, instead of 11.98, we have minus 1.25, and this is now z, and this 12.0, it becomes 1.25. Those are the z-scores that correspond to those measurements. And now we need to break this up just like we did our in-between problems in the first set. We need to look at the area to the left for the higher value, so that's z less than 1.25, and then take away the value here that corresponds to the lower value, minus 1.25, that area to the left. Now, keep in mind that just because these two are the same number but different in sign does not mean that the value here on the right is opposite the value on the left. What do I mean by that? The probability for this guy here, that z is less than minus 1.25, is not the negative of that, of z less than 1.25. So we need to be careful here in understanding that. If we look at our tables here for the appropriate values, this one here, the probability that z is less than 1.25, the area to the left of 1.25, that is 0.8944. And the area to the left of minus 1.25, we look at our tables here, is 0.1056. And now we go ahead and do our computation. We do the subtraction, and that corresponds to a probability of 0.7888. In other words, there is about a 78% chance that a mass is in this range. So notice how we already had an in-between problem, but now we casted it into the standard normal distribution used so that we could use a z-table, which is the goal of this set here. Understanding how to move from a raw specific distribution, from raw scores to standard scores. So let's look at this last example here. We have that a survey of entry-level engineers, and we have that their salaries follow a certain normal distribution with mean 70,000 and standard deviation 4,000. So let's actually jot all this down here. I will use this purple here. So the mean is 70,000 and the standard deviation is 4,000. So first I want to find the z-score corresponding to this salary, 64,500. As we saw before, that's our x. So this z will be 64,500 minus 70,000 divided by 4,000. And when we do all the work here, we get minus 1.375, but we'll just round that to minus 1.38, just because our tables work with two z-scores with two decimal places. If you want more specific results, you can use a calculator or certain statistical software. Now for part B, in fact, let me actually jot this down here before we forget. 64,500 corresponds to minus 1.38, so that's this point, maybe this point here. 64,500, that is 70,000, and I'll choose green here. This z-score is minus 1.38. And this z-score is 0. And now the z-score for the salary of 72,250. So we have x is 72,250. Okay, this divided by 4,000. And doing that work here, that comes out to a z-score of 0.5625, but we round that to just 0.56. All z-scores are in two decimal places. So this one here goes here. This is 72,250. And that corresponds to a z-score of 0.56. And so now we have two different bands here. And part C and D ask two different questions. We're not worried about an in-between this time, but we will see that we can actually transform this into an in-between problem. But for now, we'll answer what we have here. The probability an entry-level engineer is paid less than 64,500. Let's choose that one to be in this pink color here. So less than 64,500 means we're looking for an area to the left. That's this pink here. And so part C asks for the probability an engineer, let's say their pay is this random variable x, it's less than 64,500, but we've already transformed into z, so we see that this is the probability that z is less than or equal to, what's the z-score? Minus 1.38. And this is just a simple table lookup, since our tables give areas to the left. And when we look at our tables here, that probability is 0.0838. So there is an 8.38% chance that an entry-level engineer will get paid less than 64,500. Now next we have part D, which asks the probability they get paid more than 72,500. Let's go ahead and choose a specific shade of blue here. Okay. And this is this area here in blue. And it's more than, so we're looking for an area to the right. So part D asks the probability that a salary is more than 72,250. But this is an x and we already transformed into z. So we're looking for the area to the right of the z-score corresponding to this measurement, which is 0.56. And as this is an area to the right problem, we need to transform this to looking at the area to the left. And we get that by doing 1 minus the area on the left of that z-score. Okay. And when we look in the table, the area to the left of 0.56 corresponds to an area of 0.7123. And when we finally do the subtraction, that will be 0.2877. A 28.77% chance that their salary is bigger than 72,250. And so that's how we actually work with the normal distribution in specific cases. Remember to always make sure that you're drawing pictures as you go to ensure that you're getting the right answers and answers that make sense. And of course, understanding how we transform from raw X scores to specific standard Z scores.